Hello, everyone. Let's talk about topic 5, which is using similarity to find missing lengths. And to do that, let's take a look at this diagram here of what we saw back like in topic 1. In this diagram, it says we have triangle B prime, C prime, D prime, which is the image of triangle BCD after a dilation centered at point A with a scale factor 3. So a dilation happened which produced this new image. This image triangle is similar to the pre-image triangle, and therefore I can write a similarity statement. So this thing called a similarity statement, we've seen this in other examples, but all this means is we're going to write a statement that describes which triangles are similar. So I could say that the triangle BCD is similar, that's like a little squiggle like that, to triangle B prime, C prime, and D prime. And when those triangles are similar, that means that the shapes are the same. And by shape, I mean angle measure, so that the measure of the angle B is congruent to the measure of angle B prime, and the measure of angle C is congruent to the measure of angle C prime. So when the shapes are the same, they have the same angle measures, and therefore the triangles are similar to each other. So these things kind of all work hand in hand. When a dilation happens, it produces congruent shapes. When angles are congruent, it means the shapes are similar, which means that a dilation must have happened. So these things all kind of work together. And when the dilation happens and when the shapes are similar, then what we can do is we can set up the corresponding sides in a proportion, and we could use that proportion to find missing values. And what that would look like is this. When I have the triangle BCD, which is similar to B prime, C prime, D prime, and the point B corresponds to B prime and C to C prime and D to D prime, then I can write ratios like this. I could say that the side BC corresponds to the side B prime, C prime. That's a ratio of two corresponding sides. And then I can say, for example, that another pair of sides is like side CD. That corresponds to C prime, D prime. And then the last pair would be the side BD, which corresponds to B prime, D prime. Now, I didn't focus on which one had to be on top or bottom. I'm just making sure I'm consistent. This is not exactly what a scale factor would be because it's not the image lengths on top and the pre-image on the bottom, but these are just ratios, and I just wrote them consistently from one triangle to the other triangle to match up the corresponding vertices or corresponding angles or corresponding sides. So everything works the way it's supposed to here. Now, these ratios I know are equal because the triangles are similar. And I can use this proportion now to find missing values should I need to, like I'll show you in example 1 right here. Okay, so in this question, we have the triangle DEF, where the point H is on the segment DE and G is on the segment DF, so that the measure of angle E, this angle E that's right here, is congruent to angle DGH right here. Now, it doesn't tell you anything has happened. It doesn't tell you what kind of transformation has occurred, but I know that if the measure of, or the length of side DG from point D to G is 6, and from G to F is 5.25, and the length from D to H is 7.5, now I want to find the length from H to E. So I'm going to call that length X for right now. And I got to try to write some kind of equation to find that length X. Well, because I see what I see here with these triangles. Can you see two different triangles in this picture? Do you see a triangle that goes from D to G to H? And then a different triangle that they've already named in the picture, that one that goes from D to F to E? So with these two triangles, I recognize that I already have one angle in my green triangle congruent to one angle in my red triangle. Well, in addition to that one pair of angles, I can see that this angle D is the exact same angle in both triangles. So it's the reflexive property that says any side or any angle is congruent to itself. And therefore, this angle D is the same angle in green as it is in red, which means by default that this angle H is the the third angle in the green triangle, and this angle F is the third angle in the red triangle. Those two angles also have to be congruent because every triangle has an angle sum that's 180. So the three angles of the green triangle has the same sum as the three angles in the red triangle, and I know that the angle D is the same in both, and I was told that the angle E is the same as this angle DGH. Therefore, all three of the angles in my green triangle are congruent to the corresponding angles in this red triangle. Therefore, those two triangles must be similar to each other. So now, since I know based on the fact that all the angles are the same, that means the shapes are the same, that means the triangles are similar, and I'm going to write that down. That I'm going to start with triangle DEF. Okay, so the first triangle I just name however I want. Whatever three letters make up that triangle, I name that. And now I got to be very careful when I write the second triangle in my similarity statement. I know the triangle DEF is similar. That's my red triangle, is similar to this green triangle. But now I know that the angle D that's in red corresponds to the same angle D that's in green. I'm going to color coordinate this. So DEF, this is my green triangle, and this is my red triangle. Okay, so the angle D that's red corresponds to the angle D that's green. The angle E that's in the red triangle corresponds to angle G that's in my green triangle. And last, angle F that's red corresponds to the angle H in my green triangle. So now this is an appropriate similarity statement, that these points all correspond to each other. And now I'm going to use my similarity statement, because I know these triangles are similar from the angles being congruent, to write the corresponding sides in a proportion. So the side DE is in a ratio with the side DG. And that ratio is the same as the ratio of EF to GH. And then the last one I have is the side DF with DH. Now, from that proportion, I can see that in this diagram, I want nothing to do with the sides GH and FE. Those sides I'm not looking for. I don't know the length of those two sides. So what I'm going to do is, out of these three ratios, I'm simply just going to get rid of that one, because I don't need that one in order to solve what I want to solve. Okay, but what remains is the length for D to E. So how long is it from point D to point E? So there's point D and there's point E. What's the length of this whole segment? Well, the length of the whole segment is what you get when you add this part and that part. So I'm going to say the whole segment is x plus 7.5. Those are not like terms, so I can't put them together. I'm not multiplying them, I'm adding them. So the length of DE is x plus 7.5 over, now the length from D to G. So DE corresponds to DG. How long is it from D to G? It's 6. Is equal to the length from D to F. So from D all the way to F is 6 plus 5.25, or 11.25. That's the length from D to F, 11.25, over the length from D to H. D to H is 7.5. Now I have this proportion that I can solve to find the value of x. I'm going to show you a quick way to do that in another video, but you can do this by cross multiplying, but I'll make a separate video just to show you a fun tool that I found that you can use to do the algebra part of this question. See, we're done with geometry here. We know we did the geometry right here, and then by substituting, now we're just solving this algebraic equation. So I'll show you an easy way to get to this point, but what you'll find is the value of x is 1.5 when you solve. So you'll see the other video on how to find that quickly, easily, but the value of x is 1.5. Now we just got to go back and make sure that I know what it is I'm looking for in the question. It says, what's the length of the segment HE? HE has a length of x, so the length of HE is 1.5. And there's the answer to my question. Okay, so now let's take a look at some other examples. I'm going to make separate videos for each one so not to make each one too long.